YouTubers. I've got a bunch of rotary encoders here to look at. First one is a variable reluctance sensor. I've got a DC motor out of a Makita drill driver, and this is the VR sensor. It's out of a disk drive, back when disk drives were big. I've got a gap between the sensor and the gear, that's where this razor knife blade just slides in there, because I don't want to grind the end of it off. And if I've got it connected to the oscilloscope, and then I'm using these, a capacitor and a resistor, to make a filter to take out some of the noise. Let's see what this looks like. So this is driving the motor at 1 volt. You can see that's the signal coming out, and the meter has a frequency counter. It's sitting at about 250 Hertz. That gear has 15 teeth, so every revolution is 15 cycles that you can see on there. And so to get the revolutions per second, you divide by 15, and then per minute divide that again by 60. So if you look at this, you can see there's quite a bit of noise on this, but also note that this is 10 millivolts per division, and this looks like it's got peak to peak voltage of about 20 millivolts. So that's 20,000th of a volt at let's see what that is in RPM. 250 divided by 15. So it's 16 revolutions per second. It's 1,000 RPM. So this is running at 1,000 RPM right now, 15 pulses per second. If we speed it up, and we've got about 20 millivolts output. This is way under the threshold for the microprocessor to be able to read that. So I crank the voltage 2 volts. I've got 10, 20, 30, 40, 50, 60 millivolts. Crank it up again. It's 100 millivolts. That's 100 millivolts to per division. So that's right about 100 millivolts. Let's see whether we can make this thing scream. So we're getting right around a kilohertz out of it, and it looks like we've just about peaked 100 millivolts. That's 66 revolutions per second. It's 4,000 RPM. And then we're back down. We see we have a very small signal there. So that's what a VR sensor looks like. Let's look at it without the filter in there. That's kind of interesting to see how noisy that is. So this is pretty noisy. Take out the capacitor and take out the resistor, and you can see that we've got, 5 millivolts of noise on a 10 millivolt signal. So there's quite a bit of conditioning that needs to be done to clean this up, to get a clean count out of it. Let's look at the sensor. So we've got a metallic tube. It's got the sensor in there. It's been epoxied in, and it has this plastic nut on here that probably is there for not conducting, and it's pretty small. It's about 1 inch long, and 1/4 inch diameter. And there's only 2 wires that come out of it, so it's very simple. Here's another one. I think this was out of the same disk drive. It might actually be an identical sensor. Let's see what else we got. Here's a Hall effect sensor. So a Hall effect sensor has 3 pins, and you put 5 volts on one pin, ground on the other pin, and then when it gets close to the magnet, and then it'll be high, normally high, and then when it gets close to the magnet, it'll get pulled down low. And then in order to package this thing, first thing you got to do is find out which face is sensitive and bend the pins around, and then we'd slide some heat shrink on there. Probably slide that inside a soda straw like that with some epoxy, and then in turn take something like this lamp tube. This goes down the center of a lamp if you're making your own lamps. Then slide this in there, and then pack that whole thing with epoxy. This is a temperature sensor. I did something similar with. This is a nice flexi straw, and then we would end up with a sensor that's packaged pretty much like these things are already, with a tube with epoxy on it that's threaded so that you can attach it. Now here's some other sensors. These are window sensors. How these things work, these have a reed relay, and when the magnet comes close, it opens or closes depending upon which way it's oriented. These are could be good for low speed operation. Here's a relay, a reed relay sensor that's off of a piece of rotating equipment. So you can see this one has 2 pins only, and then it had a way to mount it, and then there's this shaft collar. It's got a magnet on it, and this was placed next to it, and it would rotate, and when it came around it would close the switch and it could count rotations that way. This would only be good at low speeds. I found I had a whole collection of optical interrupters. I've got some of them that are really easy to understand. These were pretty old ones because you can see that you can see the actual components in these things. So these it has a photodiode on one side and a light emitting diode on the other side. And this one with the lens on it's probably the emitter, and then the photodiode over here conducts when it sees light, and then it works just by when it's interrupted, blocks the light, so the diode stops conducting, you sense that, and so on. So you'd have a wheel that came around with a slot in it, and the slot would cross that. That's another way to do it. Let's see, what else do I have here? Here's another more modern one. This is all integrated together. This is probably out of a printer, since it looks like it's kind of got some old toner on it. Same idea. Something comes along and interrupts the beam. That makes a signal, and you count those, and a couple more. Same thing. Alright, let's see, I'm looking through my pile, see whether I have any other sensors. Oh, magnets. So the Hall effect sensor needs a magnet, and so a strong magnet can be smaller, which means that it's easier to mount it. So here's a pretty good option. You can see these things are wicked strong because I'm having a hard time getting them off. But this one is a candidate if you can drill a hole in a flywheel somewhere where you have some nice soft mild steel or something. You could drill a little hole, tap it, and put a machine screw in there to hold a magnet like that on there to pass by. And they're available in all sizes, little discs, adhesive ones if it's not going too fast so it's not going to fly off, squares, rectangles, cubes. These are from local Home Depot. That's pretty much everything I know about rotary pulse counters. For this VR sensor, the first stage would be the filter to try to remove some of that noise. Then it would go to an amplifier to get it up to above 3 volts, and then it would go to something that would clip that into a nice square wave. So there's multiple stages of signal conditioning in order to make that a nice clean signal. These other sensors, the Hall effect sensor, the optical interrupter, the read relays, they produce a nice clean, easy to read signal out of the box. They don't need any extra conditioning. VR sensors apparently are very good at high temperatures, so that if you're right by an engine block, for example, you might not want a Hall effect sensor, and that might be in fact why they're used that way. Alrighty, talk to you guys soon.